So section 11.4 is all about the cross product of two vectors in space. Okay, so something to keep in mind is that the cross product differs from the dot product completely. The dot product yields a scalar, whereas the cross product is going to yield another vector. So when we multiply using the cross product of two vectors, we're going to get another vector. So the cross product of two vectors yields another vector. And the cool thing about this vector is that it is orthogonal to both of the original vectors in the product. So it's perpendicular to both of them. Okay, so if I have got two vectors in space, we can find a plane that both of those vectors are contained in, and then when we cross them, we're going to get a vector normal to that plane or orthogonal to that plane. So the cross product is going to give us a vector that is perpendicular to both of the original vectors. Another thing to keep in mind about the cross product is that it cannot be done for vectors in two-dimensional space. It has to be three-dimensional space because we have to have that third dimension. Remember, the cross product is going to be perpendicular to both of the original vectors, so it's got to have a third dimension to go in. So it does not make sense to do this when we're limited to only two dimensions. Okay, so the cross product has a lot of different applications. For one, torque is a cross product of two vectors. So let's write that down. Torque is a cross product of two vectors. Okay, got two vectors in some plane. The torque generated by those two vectors is going to be orthogonal to both of them. So like when you're tightening a screw, something like that. Another application that's commonly used is that the magnitude of the cross product is the area of the parallelogram formed by two vectors. Okay, so what I mean by that is if I've got vector u and vector v here, if I were to close up a parallelogram using these, so I'll repeat vector v here, and I'll repeat vector u here, we get this parallelogram. Well, the magnitude of the cross product is going to be equal to the area of that parallelogram. Okay. So once again, if you'll just allow me a little bit of artistic license in my poor drawing skills, imagine that that's actually a parallelogram. Okay, so let's go ahead and define the cross product. So given two vectors in space, we have u equal to u1 in the I direction plus u2 in the j direction plus u3 k, okay, and v equal to v1 I plus v2 j plus v3 k. The cross product is u cross v, so we just use an x, just like a multiplication x. So u cross v is equal to u2 v3 minus u3 v2 in the I direction minus u1 v3 minus u3 v1 j plus u1 v2 minus u2 v1 k. All right. So that's a whole lot of information, but we can calculate this conveniently using the determinant and cofactor expansion. So let me show you what I mean by that. If we were to take, let's see here, we can calculate, let me write it down. So calculate using cofactor expansion. We're going to do a 3 by 3 determinant. So the first row is going to be I, j, k. Second row is going to be the components of u, u1, u2, U3. Third row is going to be the components of V, V1, V2, V3. Now, what vector is U and what vector is V is completely arbitrary, right? So this is the order we need to do this in if we are crossing U with V. So U cross V is equal to this determinant, all right? And we're going to use cofactor expansion here. So if you have ever found a 3x3 determinant, you probably have seen this before. So I'll do my best to run through it here. We're going to take I, and we are going to ignore the row and column that I is in, and then multiply I by the determinant of the remaining 2x2 matrix. Okay. Then we're going to do the same thing. We're going to do the same thing with J. So we're going to ignore the row and the column that J is in. And this is going to be minus J times the determinant of U1, U3, V1, V3. All right, and then finally, we'll do the same thing with K. We'll expand on K. We'll ignore the row and the column that K is in. So this is plus K times the determinant of U1, U2, V1, V2. Okay, so before I go any further, I want to address why it is that I changed to a negative sign right here in the middle. Why did I put a minus sign in front of J? And the reason for that is because we have alternating sign positions in the determinant over here in the matrix. So this is positive, negative, positive, negative, positive, negative, positive, negative, positive. So those signs are going to alternate. So we could expand on any row or column in a matrix to find this to find the determinant of a 3x3 matrix. We could do the cofactor expansion on any row or on any column. So this is just something that we need to keep in mind as we're doing that. We do have alternating sign positions. Okay. So what have we got here? Well, the determinant of a 2x2 matrix is the diagonals multiplied and subtracted. So this is going to be equal to I hat times U2 times V3 minus V2 times U3, or U3 times V2. Okay. Minus J times U1 V3 minus U3 V1 plus K times U1 V2 minus U2 V1. Okay, so we can always calculate it this way. We don't have to lug around that great big cumbersome formula up there. We can always just calculate it in this way. So let's go ahead and do an example where we use the cofactor expansion to find the cross product. So let's evaluate, this is my example. Let's evaluate U cross V, where U is equal to 7, -1, 4, and V is equal to 2, 2, -6. Okay, so we're going to go ahead and cross those. So I'm going to set up my determinant. So we have I, J, and K. So remember, these have alternating sign positions. This is positive, positive, negative, positive. Then since I've got U crossed with V, I'm going to put U first. So 7, -1, 4, and V second, 2, 2, -6. By cofactor expansion, we're going to have I times the determinant of -1, 4, 2, -6. So I'm ignoring the row and column that I is in and looking at the matrix that is left, the 2x2 matrix that is left. Minus J times the determinant 7, 4, 2, -6, plus K times the determinant of 7, -1, 2, 2. So this is going to be positive 6 minus 8 in the I, or times I in the I direction, minus negative 42 minus 8 in the J direction, plus 14 minus negative 2 in the K direction. So that's going to be negative 2I minus negative 50, so that'll be plus 50J, plus 16K. Okay, so there is our cross product. Now we can verify that this vector, this cross product that I found, is actually orthogonal to both of the previous vectors, u and v, by finding the dot product. So remember, if the dot product of two vectors is 0, the angle between those two vectors is 90 degrees, or pi. Pi over 2. So let's go ahead and double check that. So let's check for orthogonality. That's a fun word to say, orthogonality. Orthogonality, okay. Let's find the dot product. Okay, so u dotted with u cross v. Okay, that's going to be, where's u? There's 7, negative 1, 4, dotted with negative 2, 50, 16. So to find that dot product, we're going to multiply corresponding components. So 7 times negative 2 plus negative 1 times 50 plus 4 times 16. So that's negative 14 minus 50 plus 64. That is in fact equal to 0, so that checks. So let's do v. So v was 2, 2, negative 6. Dot that with negative 2, 50, 16. And we get negative 4 plus 100 minus 6 times 16. Let's see, that's 64 plus another 32 would be 96. Okay, and that does come out to be 0. All right, so we have verified that the cross product we found is in fact orthogonal to both u and v, so we probably did that correctly. We did do it correctly, but it's a good way to just quickly double check yourself. The probability of getting another vector that's perpendicular to both of those that is not the cross product is extremely slim, like almost non-existent. So if these check out, you know you're good. Okay, so let's now jot down some properties of the cross product. So this is a couple of different theorems in our book. So let's see, props of the cross product. Okay, number 1, u cross v is equal to the opposite of v cross u. Okay, so this is not commutative. The cross product is not commutative. If you cross u with v, you'll go one direction. If you cross v with u, you'll go the opposite direction. So again, think about turning a screw. If you turn it in one direction, it's going to go in. If you turn it the other direction, it's going to come out. It's because the direction that the torque is going. Okay, number 2, if I have u crossed with v plus w, that's going to be equal to u cross v plus u cross w. I'll put parentheses around these so that they're easy enough to see there. Okay. If you have a scalar, c times u cross v, okay, that's equal to c times u crossed with v, or it's equal to u crossed with c times v. If you cross something with the 0 vector, the result is going to be the 0 vector. So u crossed with the 0 vector is the same thing as 0 vector crossed with u is equal to the 0 vector. If you cross a vector with itself, you are going to get the 0 vector. And if we take the dot product, u dotted with a cross product v cross w, that is going to be equal to the same thing as u cross v dotted with w, okay? And that's actually called the triple scalar product. So we're going to talk a little bit more about that in a few minutes. Okay, number 7. U crossed with v is orthogonal to both u and v. Okay, so we already talked about that. Number 8. That is a 7 right there. There we go. Number 8, the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between those two vectors. Okay. So that's something else that we can use to find angles between vectors. Number 9, if u cross v is equal to 0, then u and v are scalar multiples of each other. Okay, and that's actually an if and only if statement. If u and v are scalar multiples, in other words, if they're parallel, then when we cross them, we are going to get 0. And finally, number 10, the magnitude of u cross with v, as I said earlier, is equal to the area of the parallelogram formed by u and v. Okay. So again, we mentioned that one earlier. So it's good stuff, very good stuff. All of these properties are going to be very useful to us as we are working through this section. Okay. So let's go ahead and do another cross product example. Let's go ahead and find the area of the parallelogram formed by u equal to 2I minus 2j plus k, and v equal to 3I minus j. All right, no problem. Except there's a problem, right? Because we said that we can only do this for three-dimensional vectors. So we're going to have to write v as a three-dimensional vector. Just because it lies in the xy plane does not mean it's not a three-dimensional vector. We just have to think of it in space. So we're going to think of v as 3i minus j plus 0k, right? So it is a three-dimensional vector. And we can go ahead and find the cross product of these. So u crossed with v is equal to the determinant ijk of u 2, negative 2, 1, and v 3, negative 1, 0. Okay, so now, does it matter which one goes first here, u or v? And the answer is no, it does not matter. Whenever I get this vector, whether the vector is positive or negative, that really doesn't make sense when I'm talking about vectors, but regardless of which direction I point that vector, that's what I mean by the positive or negative, whichever way that vector is pointing, the cross product that we get, it's irrelevant because we're going to find the magnitude of that vector to describe this area. So I can choose to put v first and cross v with u, or I can choose to cross u with v. It does not matter. Okay, so let's do our cofactor expansion. So this is going to be negative 2 times 0 minus 1 times negative 1, that's the I direction, plus, oh, not plus, remember, minus, we've got our signs alternating, so positive, negative, positive, minus 2 times 0, get my colors straight here, 2 times 0 minus 1 times 3, j direction, plus 2 times negative 1 minus negative 2 times 3 in the k direction. So that's going to be positive 1i minus negative 3j, so plus 3j, plus negative 2 plus 6 would be positive 4k. All right, so there's our cross product, and now it's up to us to find the magnitude of that vector. So the magnitude of u crossed with v is going to be equal to the square root of 1 squared plus 3 squared plus 4 squared. So that is the square root of 1 plus 9 plus 16, which is the square root of 26. That does not simplify. So there's the area of our parallelogram. All right, so now we're going to talk about the triple scalar product. So let's go ahead and write that down. Triple scalar product. This is where we dot a vector with a cross product. So U dotted with V cross W, or U cross V dotted with a vector W. Okay, either way, you're going to get the exact same thing. All right, so that cross product given U, V, I'll go ahead and write it down. So for U equal to U1, U2, U3, V equal to V1, V2, V3, and W equal to W1, W2, W3. Okay. The triple scalar product is equal to the following: U dot V cross W. Okay, it's equal to the determinant of U1, U2, U3, V1, V2, V3, and W1, W2, W3. Okay. So this makes perfect sense. So before we were finding the cofactor expansion, we're going to do the exact same thing here. Remember, keep in mind that these are alternating sign positions. Okay. The dot product is multiplying corresponding components, yes? So if you go back and look at what we had previously, when it came to finding a cross product, we were finding components and multiplying those components times vector I, times the unit vector I, times the unit vector j, and the unit vector k, right? So this is very analogous to that. Instead of I, j, and k, we're multiplying by the components of u, u1, u2, and u3. So it's going to come out to be exactly the same thing as the cross product using I, j, and k, except instead of multiplying those components by the individual directional vectors, unit vectors, we're going to be multiplying it by the components of u. Okay. So this comes out to be u1 times v2w3 minus v3w2 minus u2 times v1w3 minus v3w1 plus u3 times v1w2 minus v2w1. Okay, so really it's very much the same thing as what we had before, only instead of I, j, and k now we have the components of u, u1, u2, and u3. Get that all on screen for you. Okay, so what's the point of this? Well, it's kind of interesting. Just like the cross product of two vectors gives us, or the magnitude of that vector, rather, the magnitude of the cross product is going to give us the area of a parallelogram formed by two vectors. The absolute value of this dot product, or triple scalar product here, is going to be the volume of the parallelepiped formed by the three vectors. So that's kind of cool, kind of interesting. So let's write that down. The triple scalar product U dotted with V cross W gives us the volume of the parallelepiped formed by U, V, and W. And that volume is just equal to the absolute value, because the scalar product could be positive or negative, right? But if we take the absolute value of that, we're going to have the actual volume. Okay, so there it is. So this is a scalar, right? The triple scalar product, it's in the name, scalar. It is a scalar because we are getting a vector and we are dotting that vector with another vector, and the dot product comes out to be a scalar. And that scalar, if you drop its sign, if you ignore the sign, is just the volume of the parallelepiped formed by those. And if you have not said parallelepiped today, you need to say that word. It's just a lot of fun to say. Okay, so let's do an example. Go back to white, example. Find the volume of the parallelepiped formed by U, which is 131, V, which is 066, and W, which is -4, 0, -4. Trying to fix this W. It's driving me crazy. There we go. There's a W. Okay, so we're going to find the volume. Oh, and if I wasn't clear about it, if I glossed over that, the parallelepiped, it's kind of like what you think of as a parallelogram in 2 dimensions, but shifted into 3 dimensions. So it's kind of like a prism, right? Not necessarily with any right angles or anything, but you know, some kind of a box that could be laid around and shifted and stuff in 3 space. Okay, so let's do this. So U dotted with V cross W. First thing we're going to need to do is, well, I started to say the first thing we need to do was cross V and W, but that's not true because we can just do this all in one big fail swoop. So if you like finding the cross product and you're really good at that, and you can do it just by looking at V and W, you might find that first and then go ahead and dot that with U. I'm going to do it using the definition we had earlier. So I'm going to put in U, 131, V, 066, and W, -4, 0, -4. And I'm going to do a cofactor expansion along the top row. So that's going to be equal to +1 times the determinant. Let me actually write this out so you can follow along with me. The determinant 6, 0, -4 minus, so let's again, don't forget, we are using alternating signs here. Plus, that's a plus, minus -3. Oh, see, there's the danger in writing that down. -3, there's the minus, there's the 3. Oh gosh, times the derivative, or the determinant of 0, 6, -4, -4, plus 1 times the determinant of 0, 6, -4, 0. Okay, all right. So let's see here. So this is going to be 1 times 6 times -4 is -24 minus 0, minus 3 times 0 minus -24, plus 1 times 0 minus -24. So that's -24 minus 72 plus 24 is equal to -72. Okay, so the absolute value of that is equal to 72. So the volume of this parallelepiped formed by these 3 vectors is 72 cubic units, whatever those units are. But since we weren't asked to give units specifically, we can leave it just at 72. And that wraps it up for this section. As always, if you have questions, please let me know. You might want to refresh yourself on cofactor expansions if you don't remember how to do that. And yeah, that's it. Oh, wait, one more just quick note. I have been misspelling parallelepiped. It is Parallelepiped. So that's my bad spelling error. Okay, so just in case you wanted to know.